How are we doing on elimination reactions? Any questions to begin? We looked at dehydration of alcohols using a strong acid in which the nucleophile is not going to do anything, like H2SO4. Or HF, because F minus we said to poor nucleophiles, but HF is a fairly uncommon reagent in the lab, sulfuric acid is much more common. Dehydration of an alcohol by an E1 mechanism. Okay. Protonate, ionized to make carbocation. E1. Of course, alcohols do not undergo E2 reactions, right? Why do alcohols not undergo E2 elimination? Porsche? Why do alcohols not undergo E2 elimination? Well, you can make OH. Good leaving. OH is not a good leaving group, I agree. But in E1, we make it a better leaving group. So, explain further.
Would it just reverse the reaction and do a substitution immediately, or no?
No, I'm not quite sure what you're describing. What do you mean substitution?
So, because it would break off and most likely combine with a cation.
It wouldn't do anything.
Okay.
Because you need a strong base for E2 reactions.
Because strong E2 requires a strong base. That's correct. And?
And if you use a protonate, the OH you need an acid, and the acid you have a base instead.
And you can't have your cake and eat it too. You cannot have a strong acid and a strong base in the same reaction. How do you make OH a better leaving group? Protonate with what? Strong acid. E2 requires strong base. Incompatible. You can't do an E2 with an alcohol, but you can do an E1 because you can protonate it, then it can ionize and make carbocation, and then you can put in the double bond in the fast step. Okay? E1 elimination, dehydration of an alcohol. Very common reaction of alcohols to make what? Make alkenes. That's the opposite of what we did during test 2. During test 2, we hydrated. Well, it's not the exact opposite. If you hydrate this, are you going to get that? If you do the exact opposite? With H2SO4? Final exam is in a week or two, yeah? Will hydration of that alkene give that alcohol? What's going to be the difference? What are you going to get? You're going to make carbocation down here, and then you'll end up with the OH here, Markovnikov hydration. To go backwards, instead of using something like that, what do you need to use? Hydroboration oxidation to get the anti-Markovnikov alcohol coming from there. But we do know how to hydrate alkenes, which is the reverse of, what's the reverse of hydration? Dehydration, right? Okay. Moving on. Other miscellaneous comment. We need to make sure we make this comment. We've sort of said it along the way. A more steric and hindered base will favor elimination over substitution. What is 3? What are we doing? 1, 2. What is 1, 2, and 3? When either one is possible, what's going to occur? Well, here's a third thing to consider. A more steric and hindered base will favor elimination over substitution. Okay? Well, we've already kind of said that. The more sterically hindered your nucleophile / base is, That's going to hurt SN2. We could ask questions like this. If you wanted to eliminate here and make the alkene, which base is best? Ammonia, sodium hydroxide, or sodium butoxide?
Sodium hydroxide.
Yes, be your best base. Why are the other two not as good? Why are the other two not as good? The other two are not as good because they could do a substitution. The leaving group's on a secondary carbon. If it was on a tertiary carbon, choice of base wouldn't really matter. It's going to do E2 no matter what. But it's on a secondary. You can do SN2 on secondary. So you like to use a more sterically hindered base. So it will only give elimination. Do you have to worry about getting alkene isomers like Hoffman or Zaitsev in this reaction? Why not?
Because the other carbon doesn't have a beta hydrogen.
Very good. The other carbon doesn't have a beta hydrogen. The only way to eliminate is right here. So we don't have to worry about this being too sterically hindered and getting some other isomer. There is no Hoffman-Zaitsev. It's not relevant here. Okay, moving on to G. Clever ways to make ionization of an alkyl halide to the carbocation faster. Of course, if you're talking about carbocation, we're talking about E1 or SN1. Now, typically, like a bromine, we just say it's a good leaving group. We never had to make it a better leaving group, like an OH or something else. Okay, iodine, good leaving group. Tosylate, good leaving group. You don't have to do anything to them. All right? But sometimes, though, maybe the ionization will be a little slow. You know, secondary. It's not going to be as fast as tertiary. And for some reason, it might be a little slow. And of course, if it was primary, it'd be super slow, and it wouldn't happen in our class. We'd just not do that. Okay, a little slow. Is there any way to speed it up if it's a little slow? Well, you do not protonate halides like you do alcohols. They don't react with acid, and you're not going to do that, okay? One clever way you can do, though, is you can use a Lewis acid. What's the definition of a Lewis acid? Not a proton acid, not a Bronsted-Lowry acid. What's a Lewis acid? Definition. No, not an electron donor. Lewis acid, electron acceptor. Okay? Any acid is an electron acceptor. Even if you do Bronsted-Lowry. H plus. If these react, which one's the acid? These electrons make bond here. Yeah? Well, that's accepting these electrons. But we call it a proton acid. Bronsted-Lowry acid, it's a proton. If it's something else, we call it a Lewis acid. Common Lewis acid for halides is silver ion, Ag+. Ag+. Analogous to H+, but it's a metal ion. Okay? And the lone pair on a halogen will coordinate with the silver plus, just like this here. Acid-base reaction, Bronsted. Anytime we say acid-base, we've always been doing Bronsted acid-base. Okay? These coordinate Now we could show this sort of the same way, like this, and that's going to give bromine now coordinated to the silver, 2 lone pairs left. The other one became bonding pair. The bromine now has what charge? Bromine is now positive. Silver is now neutral. All right. This over here, the oxygen becomes positive. Yeah. At this point, the bromine would really like to get its lone pair back. Now this could go backwards, but it can also take these 2 electrons and get its lone pair back. Now the bromine will be more eager to leave the carbon. And when it leaves the carbon, what do we get? We get our carbocation plus what? Plus silver bromide. Okay? Now you can consider this ionic or possibly covalent. It's a transition metal. A lot of transition metals do bond more covalently.
Can you do the same thing with fluoride even though it's a poor leaving group by itself?
In specialized cases, we won't do it in this class. We'll make a comment. Okay. Now what do we know about silver bromide? Now this is aqueous. A lot of times this is going to be aqueous. It has to be aqueous to get your silver ion dissolved, most likely. Silver bromide is not soluble in aqueous. It's going to precipitate. What's a better leaving group? A positive bromine, a neutral bromine, or a positive bromine? Positive. It's like, I got to get my electrons back. I'm going to leave, okay? And you can show the bromine now has its full octet back. Well, it has octet here. It has its 3 lone pairs, or 4 if you consider it ionic. I showed it covalent here. It's okay with a transition metal. You do not do this with proton. One reason you do it with silver is halogen and silver makes a very strong bond. They like each other a lot. Okay? And they come together, they coordinate, okay? Certain elements in chemistry just like each other, and you often see them sort of making strong bonds and wanting to bond together. And that's why it's not soluble in water, because it doesn't want to break apart. It just, all right? Very strong ionic bond or covalent, whatever it is. You know there's an intermediacy between covalent and ionic where it's sort of halfway between each. Okay, there's a continuum there. But there's lots of elements that love each other. You mentioned fluorine. Okay. Silicon is often sometimes used as a Lewis acid for fluorine because fluorine and silicon really love each other. That's one reason that fluorine will etch glass, because glass is largely silicon-based. The fluoride will react with the silicon, and you'll start degrading the glass and etching it something. Halogens and silver, oxygen and phosphorus. Okay. Very strong bonds. Oxygen and boron. There's a variety where you often just see things, and you often see chemistry associated with these strong. Okay, so what's the definition of the silver ion? Here? It's a Lewis acid. It accepted the lone pair, as opposed to a Bronsted-Lowry acid. Now there may be some other metal ions that will do this. Silver is the most common. In organic 2, we will see aluminum and boron used in the same way to get carbocations. Now we use silver nitrate here because it's soluble. Okay. You remember your solubility rules, just I think all nitrates are soluble in water, is that right? Including silver nitrate. It's soluble, but when you do this, you're going to end up with a precipitate of silver bromide because it's not after it rips out the bromine. Okay? Ripping it out, it's a very scientific term, yeah? So this is a clever way to get your carbocation faster. Use a silver ion or Lewis acid, such as silver ion, not proton. Now the use of the silver can also be used as a chemical test for the presence of bromine or halogen. You did this in lab when you made your T-amyl chloride. Okay, you reacted it with silver nitrate, got a precipitate, yeah? Because basically the silver ion complex with the chlorine and then the chlorine ionized off and made the carbocation. You didn't see the carbocation, it stayed dissolved or it eliminated or did something. What you did see though was the silver chloride that precipitated. Okay? You didn't see this, it did something. Maybe water reacted and it went back to the alcohol, maybe it eliminated, whatever it did, you didn't see that. But you did see the precipitate form of silver chloride in that case. And so since you saw something, that's a visual test. And you're only going to see that if there's ionizable halogen present. Because that's the only time that that chemistry will take place to give you the precipitate. So it can be used as a chemical test for ionizable halogen. Question: which compounds below would give a positive silver nitrate test? Which ones will give a precipitate of silver bromide if treated with silver nitrate?
The first one and the third one?
First and third?
That's my guess, yeah.
Why the first?
Because it'll make a tertiary carbocation if it
No.
second and third.
No, it won't be tertiary. This carbon's bonded to two carbons.
Oh,
But it's no good.
the third one?
No good. The bromine is on what type of carbon? Is that tetrahedral?
No.
No. And the leaving group for any of these reactions must be on what type of carbon? Tetrahedral. Okay? Leaving groups are not going to leave an sp2 carbon. That's not a leaving group. A bromine is only a leaving group if it's on a tetrahedral carbon. Now we could talk more why. You can substitute this, but that will be not SN1 or SN2. Okay, there are more substitution mechanisms out there. SN1, SN2 are for tetrahedral carbons. Leaving group is on an sp2 carbon, it has to be substituted by another mechanism, such as a benzyne mechanism. No, this is not going to ionize. You're not going to make carbocation here. And thus you're not going to form silver bromide because the silver is not going to yank the bromine out. No. The other three, yes, though. The other three will give a precipitate. Bromine gone, secondary cation, bromine gone. Well, let's ask the next question. Of those, the three, which would give the precipitate the fastest? What's the question, really? Question is, which one's going to make the best carbocation and which one does form fastest? Which one? This one, why?
Tertiary.
It would be tertiary. Not only would it be tertiary, it would be
Resonance stabilized.
resonance stabilized. And you can see the little windshield wiper. Yeah? This would be a secondary cation. This would be tertiary with resonance. And this would be what? Are we even going to make cation here? We would. It's secondary with resonance, right? That's confusing. What type of carbocation are we going to make over here? Somebody said no. What type of carbocation are we going to make over here? Primary, secondary, what?
It's like primary.
Is it primary or is it what?
It's going to ionize off and it's going to resonance stabilize back to secondary.
Right. When it ionizes off, it's going to be primary, but it's resonance stabilized. You can do resonance and the cation will be here, it's secondary. So is it primary or secondary? It's both, it's a blend, it's a hybrid. What it's not is just primary, because we would never make just a primary cation in this class. We said that's bad. That's not just a primary cation. You could actually call it a secondary cation if you want to show that resonance structure.
So then the other one's not necessarily tertiary either, is it?
Good point, because if you do resonance, you're going to put secondary. It's a blend of tertiary, secondary. But which resonance structure would be more favored?
Tertiary.
The tertiary structure would be more favored of the hybrid. Which resonance structure would be more favored over here?
Secondary.
Right. So don't look at it and think it's just a primary carbocation. Because once resonance is there, it becomes a blend. And when you have a blend, maybe the other one is the major contributor. Okay. Yeah, I would expect this one to form fastest. All right, number 2. What are we under? I think clever ways to make a leaving group better, is that right? Use a polar solvent. We haven't talked much about solvents. A polar solvent is going to promote ionization of the leaving group. Yeah? If you take this alkyl bromide and react it with this alcohol, in a polar non-nucleophilic solvent, such as acetonitrile and DMSO, what's acetonitrile? What's acetic acid? Acetonitrile and acetonitrile, acetic acid. That's acetic acid, right? CH3, acetic acid. Acetonitrile is that there. It's a common polar solvent. You have dipole. This, of course, might be written like this, CH3CN. You don't have to write all this down. I often write it like this. It's a methyl group bonded to a cyano, yeah? Different ways to show things. Acetonitrile. DMSO. And both of these are probably on the solvent handout I gave you back in August. Dimethyl sulfoxide. Pretty common solvent, particularly for these types of reactions. A sulfoxide is a SO, and it's dimethyl. It's actually analogous to this compound. Carbon here, carbonyl instead of the sulfoxide. What's the name of this compound?
Ketone. Dimethyl ketone.
Dimethyl ketone is probably a bottom tier name here, but you can name ketones like that. Methyl ethyl ketone is actually a common name, commonly used for that compound. We'll learn how to name ketones in organic too, but what's the name of that compound? It's got a common name. You can't pass organic 1 if you don't know that right there. That's a department criteria. It's on the syllabus. You cannot pass this course if you don't know the name of this compound. All right, we'll try again on Friday.
Is it dimethyl ether?
No, it's not an ester, that's a ketone. Dimethyl ketone is what he said, but that's not the common name in this. Somebody?
Acetone?
A little louder?
Acetone.
Acetone? Yeah, it's acetone. Congratulations, you may pass. Depends on the grades. But you passed criteria number 1. Anybody ever used acetone before?
Yeah.
You know the structure of this compound you're using? Not supposed to use compounds if you don't know structure and safety. All right? So DMSO is a lot like acetone, but it's got the sulfur. Tends to be more polar. It's got a long pair here, yeah. You know those structures, yeah. Sulfur has 6 electrons around it, yeah. So these are a couple of polar solvents. There's others. If you try to do this, so we can get a product here, looks like the alcohol replaced the bromine, yeah? What mechanism is that, most likely? It's a substitution, yeah? Because under my hand used to be a bromine, and that's the oxygen. Substituted. We made HBr, we can predict that mechanism. That should be quick, guys. Mechanism for that. Mechanism?
Wouldn't it be SN1?
John?
SN1,
Why is SN1?
because it's not a strong nucleophile.
Because there's no strong nucleophile. You've got to have a strong to do SN2. Strong nucleophile for SN2, strong base for E2, yeah. Yeah. What's the rate determining step in this mechanism up there?
The leaving group ionizes.
Leaving group leaving? We're under some letter. I think the title of it is Clever Ways to Make the Leaving Group Leave Faster, Easier. Okay? Use a polar solvent. That will help it. If you do this reaction with a non-polar solvent such as hexane, probably not going to get a reaction. Because when this thing leaves, what are we forming? Carbocation. Carbocation is going to be, hexane is not going to like carbocations. It's not going to help it. You see, when these things form, the solvent can help them form. The solvent can give them some love and start coordinating with it. Okay? The DMSO, this lone pair can kind of coordinate here. It's not going to react. You could maybe say, well, why doesn't it react? Well, that's a great question. But any of your reactions, your solvents are there doing stuff, coordinating by IMFs. Okay? And the coordination is going to help stabilize this and make it happy and help it to form. That's why when you put HBr in water, what does it do? Or HCl? It ionizes. But guess what? If you put HBr in hexane, it ain't going to ionize. Because hexane doesn't like ions. And it's not going to give the ions any love. Hexane is not, okay? You need a polar solvent to facilitate formation of a polar carbocation. It is polar, right? Are ions polar? Kind of definition of polar, I think. I haven't had physics in a long time. By the way, whenever there's a plus, there's got to be a minus. What's the minus? I made carbocation, what's the minus? The Br minus, yeah. I mean, you have polarized, you turn this into 2 ions. That's the definition of polar. I see extreme polar. I mean, it's already polar from a dipole, but when it ionizes, it becomes extremely polar. thing doesn't like mixing the polar, so that's not going to help that. Probably not going to react. Okay? So, polar solvent is going to facilitate ionization. Okay, moving on. H. Very different topic here. Let's look at something called deuterium isotope effect. This is a neat way to determine if an elimination reaction is E1 or E2. Isotope effects can be used for lots of things. To study mechanisms and rates. Here I'm going to show you how you can look at it to determine if it's E1 or E2 mechanism. Okay, consider this reaction. You take this substrate, react it with this guy. Anybody know the name of that? Benzene with a nitrogen instead of one carbon. Pyridine. Okay. It's kind of a weak base. I wouldn't call it strong. It's sp2 nitrogen. Often used as a weak base. We've got an elimination product here. Looks like the pyridine took the H. Leaving group, we made that salt there. Elimination, is this an E1 or E2? E1 or E2? Why E1?
You said it's weak base, and also that looks like the safe set to me. And doesn't E1 always make safe set?
Yeah, but E2 also makes H2.
Well, you said it was weak, so that's...
E2, H2 is always preferred. The only thing is with E2, sometimes you don't get the preferred. E2 can sometimes give the Hoffman. So you can't just look at it being H2 and tell. If it was Hoffman, then mechanism had to be what? E2, because E1 never gives Hoffman. E1 always gives H2 because that's the best product. And we didn't really point it out, but E1 is thermodynamically controlled. We could look at further why always H2, but we just sort of made that statement. Okay, so the question is really, is this strong enough to do an E2? Now, I kind of said it's weak, but I was kind of borderline. It's a borderline base. So is it E1 or E2? Maybe it's E2. Maybe pyridine is strong enough. Is there a way we can determine this with E1 or E2? Yes, deuterium isotope effect. It's a neat way to determine if it's E1 or E2. But before we look at this, what's another way we could have done this? One we've already talked about. We could do rate concentrations. What do you want to change the rate of? Brian, what can we change the rate of? I mean, change the concentration of?
Pyridine.
Okay, and then what do you expect? Explain how this is going to help.
If the rate increases, then pyridine is an E2 reaction.
If the rate increases, then
Then it's an E2 reaction.
very good. We can do the reaction and get a rate. Then we can come back and do it again, maybe double the concentration of the pyridine. We double the concentration of the pyridine and the rate doubles. That tells us the pyridine's in the rate determining step, and thus the mechanism is E2. What if we double the pyridine and the rate stays the same? It must not be in the rate determining step. Thus it must be E1. Yes. And that's number one here. Number two, though, is deuterium isotope effect. Something below? Yes. We do this reaction with a deuterium here at the beta carbon instead of hydrogen. Now you would have to make this, and this could be difficult to make. Sometimes it's easier than or not. Getting the deuterium there is not trivial. But if you can get the deuterium there, then do the reaction, and then ask, With the deuterium there, is the reaction faster or slower or whatnot? Here's what we need to know. The CD bond is stronger. Okay? The CD bond is stronger than the CH bond. That's stronger. And here's an important question. In which mechanism is the carbon beta hydrogen bond broken in the rate determining step? E1 or E2?
E2.
In which mechanism is the CH bond broken in the rate determining step? What's the rate determining step of E1? Leaving group leaving. Leaving group leaving. That, right? Same as SM1 rate determining step. Did the CH or CD bond break in that rate determining step? No. What's the rate determining step for E2? Don't try to write this down. I'm going to erase. I'm going to repeat here, and you'd have to redraw it. E2 would be what? All together now. Concerted. There's your rate determining step. Is the CD bond broken in that step? Yes. The carbon beta hydrogen bond is only broken in the rate determining step if the reaction is E2. If this bond is stronger, it's going to make the E2 more difficult. But it will not make the E1 more difficult. Because that bond is broken in the fast step into E1. Basically what you do is you get your hands on the deuterium compound and do it. And if deuterium here slows the rate down, that tells you that that bond is being broken in the rate determining step, and the mechanism thus must be E2. This is called an isotope effect. We went to a different isotope, and it led to an effect. Because the CD bond is stronger. Why is the CD bond stronger? It's called a mass effect. Deuterium has a mass, it's 100 times, it's 2 times greater than, it's double of hydrogen. And in terms of isotopes, that's huge. If we go from carbon 12 to carbon 13, that's not doubling the mass. That's only 1/12 increase. We didn't go to carbon 24. But when you go from 1H to 2H, that's deuterium, you're doubling the mass. That's a huge effect because the mass does influence the bond strength. And again, I haven't had physics in a long time, but you might ask that in physics. But mass does affect bond strength. And so it's because of the mass. I think the CD bond is about 7 times stronger than a CH bond, I think. Okay. So, you do remember what deuterium is, right? Isotope of hydrogen. This is sort of looking at isotopes and an isotope effect, mechanism, rate determining step, variety of things here. Actually, deuterium is being used more and more in drugs. Why? Same reason. Same reason. Same type of reason. On the back here is an HIV drug. And this was an original. But this drug is metabolized. And when it's metabolized, the metabolite is no longer active. And that could be bad in some cases because maybe you want the drug to last long. If it's metabolized quickly and it becomes inactive, then you got to take the pill over and over. You may have to take it 4 times a day, and that leads to compliance issues, and et cetera, et cetera. Basically, if you want the drug to last longer, you would want to inhibit the metabolism. This drug is metabolized by introducing a hydroxy group at this position in the pyridine ring. But when this is introduced, the drug is no longer active. One way that the drug companies and the chemists have tried to stop the metabolism or slow it down is to replace this H with a deuterium. Now when you metabolize, you have to break the CH bond. Instead of CH, it becomes CO. And so the CH bond is gone, it's broken. But if it's CD, and that's a stronger bond, it's going to be more difficult to break that bond. And the metabolism will thus be slowed down. This is assuming that that bond is broken in the rate turning step. But I think this compound, I don't know what's below here, but I think this compound has been remade with the deuterium here, and the metabolism is slower and it lasts longer in the body now. So this is kind of a trick, a little tricky. This is scientists sort of being creative and innovative and using chemistry to create better drugs, etc. Yeah? Drug design. All right? Where we at? Back over here. Provide both substitution and elimination. How are we doing these? Any questions about these? Any questions about those guys? Okay, let's look at final topic here, double E2 elimination. No, it's not a new James Bond movie, it's a way to make alkynes. These substrates both have two leaving groups. This is a vicinal dihalide. Remember vicinal dihalides? We can make them from a certain way. We saw how to make them. Yeah, the chlorines are not on the same carbon, but they're next door. They're like in the same vicinity. Halides on the same carbon, that's a geminal dihalide, like twins, Gemini. All right? In both cases, these can be converted to alkynes. Double E2 elimination. We've got a strong base. All right? Which one's going to be eliminated first? It's hard to know, but what do you think? Which halide is going to be eliminated first? Any argument you can make here? If we eliminate this chlorine, where's the beta hydrogen? Not there, but here, yeah? If we eliminate this one, where's the beta hydrogen? Here, yeah? Okay, you got two equivalents of the base. At the very beginning, which H is the base going to take? Any argument you can make?
On the bottom left.
Why that one?
It's easier to use.
More accessible. Yeah. Think so. Take this H. E2, anticoplanar. But there's two H's here. Remember when there's two H's, we really don't have to worry about it. It's going to be in the right conformation. It's going to eliminate. I'm not really showing conformation here, but it'll be going to get the best one. That's going to give better alkene here and here. Can this guy eliminate? We're going to make an alkyne. Make that. What did we just do? We removed HCl. If you eliminate HCl again, we can get that alkyne, yeah? Down here, if we eliminate HBr, strong base, we're going to get boom, boom, boom. And if we eliminate again, boom, boom. Third alkyne between here and here, eliminate HBr, alkyne here. This carbon is now linear. Got to be careful. I wouldn't want to draw that like that. This carbon and carbon bond is now linear. I'd want to draw the alkyne like 1, 2, 3, 4. Minus HBr. You can eliminate twice here. But what's peculiar about the second elimination, though? What seems to be wrong? Or what are we doing there that we shouldn't be doing? And we're out of time, guys. What's wrong with that over there? It does happen. It can happen. It requires a little extra heat, a little extra energy. But what's wrong there? And I'm saying it at the very end because we've said no, no, no. Of course, everything has an exception. It's an exception. What's the exception over there? The leaving group in the second elimination is not on a tetrahedral carbon. I almost hate to show that to you because I hate to show you the exceptions because then you're going to get in trouble. Don't ever do that except for here. All right? That's, all right? I don't want you to go doing it anywhere else. That's why when you did a double E2 elimination, it had to be heated pretty high. Question?
Where did you put all of them? Did you just forget that?
Thank you, yes. And you said phenol?
Sorry.
Not phenol, phenol. All right. Yes, very good. Very good. This has a phenol on the end carbon. There should be a phenol here. I also turned this butyl into an isopropyl. Anybody else see that? Okay, see you upstairs in lab this week. We'll be checking out. Have a good day, guys.